Okay, good evening, students. So today is the TSPSC AEE exam day, for which many of you have prepared really hard over the last 2-3 months, and I hope it went well. So now you can relax and chill out for a few days before again getting started with your preparation for the next upcoming exams of GENCO and TRANSCO. Anyway, here I've got all the questions of analog circuits from today's AEE electrical paper, of course. And altogether I could find about 14 questions. So in this session I'll just quickly go through all the questions, and wherever required I'll give you some sort of explanation. So on the screen we have the first question. Find the type of filter shown below. So there is an op-amp circuit and nothing is given about the op-amp, which means the op-amp can be assumed to be ideal. And also the circuit has got only one capacitor. So the given circuit is a first order circuit, and any first order circuit can be low pass, high pass or all pass, but it cannot be band pass as well as band stop. So from the options we can directly rule out band stop and band pass. So now we have to choose between low pass and high pass. So how do you decide low pass or high pass? By simply finding the output or the gain at low and high frequencies. So first let us find the gain of this circuit at low frequency. At low frequency, at low frequency the capacitor behaves like an open circuit. You can simply remove the capacitor like this, and then let us find the output. See, whatever be the frequency, the op-amp will always be in negative feedback. So from virtual short, V plus and V minus both will be equal. So the voltage at the plus input terminal from voltage division is going to be Vi by 2. Now if V plus is Vi by 2, then V minus is also going to be Vi by 2. And of course this input current is again going to be 0. So what is this current going to be? Vi minus Vi by 2, which is Vi by 2 upon R, or Vi by 2R. Now this Vi by 2R will flow through this R. So even this current is what Vi by 2R. And the resulting drop across R will be Vi by 2. Now this is Vi by 2, then you have a drop of Vi by 2. Vi by 2 minus Vi by 2, V0 is 0. So at low frequency, the output is 0. If the output is 0, even the gain will be 0. So here itself we can say that the given circuit is a high pass filter, but still let us go ahead and find the output at high frequency. So the second circuit we will analyze it when the input is at a high frequency. Again, high frequency, generally the capacitor tends to behave like a short circuit. So this time we can replace the capacitor with a short circuit, that's all. Whatever be the frequency, the voltage at the plus input terminal will be Vi by 2. Then from virtual short, V minus will also be Vi by 2. Now the minus input terminal is directly shorted to the output. So V0 is also Vi by 2. So V0 is Vi by 2, then what is the gain? It is half. So you can see at low frequency the gain is 0 and high frequency the gain is half. So clearly it is a high pass filter. So the correct answer is option C, high pass. Moving on to the second question, I'll just read it out. Find the polarity of op-amp input for negative feedback operation. So there is some op-amp circuit, and the circuit contains what? An op-amp, a transistor, an NPN transistor, along with a DC current source. And the two input terminals have not been marked plus and minus. So you have to decide which one should be plus and which one should be minus, such that the circuit will have negative feedback. Again, this is based on a very simple fact that for negative feedback, the loop gain should be negative. Obviously, for positive feedback, the loop gain should be positive and so on. And loop gain, as I always say in the class, it is what the gain around the loop. So if the loop gain is negative, then only the overall circuit will have negative feedback. So let us just go around the loop. Let us start from this point. Let us go from here to here. See, if you are going from here to here, through the transistor, you are actually going from base to collector. Base to collector, which means we have some sort of a common emitter amplifier. Then again, let us go from here to here. We are simply going through a wire whose gain will be +1. But the gain of common emitter amplifier will be negative. And then from this point, let us come back to the starting point. And remember, our requirement is what? For negative feedback, the loop gain should be negative. Already in the loop, there is one path which has a negative gain. The remaining gain has to be positive, which means the gain of this path, that is when you go from A input of the op-amp towards its output, should also be positive. And for that, A must be the plus input terminal. So obviously B must be the negative input terminal. Then only the loop gain will be negative and the circuit will have negative feedback. So A should be plus input terminal, B should be minus input terminal, which is option B. Okay. Look at the third question. What is the time period of oscillation of V out? First of all, the given circuit, it is what the very popular relaxation oscillator, which is based on the Schmidt trigger along with an RC circuit where the capacitor will get exponentially charged and discharged between the two trip points of the Schmidt trigger. So what are the two trip points of the Schmidt trigger? So UTP, the upper trip point, will be Vsat times R1 by R1 plus R2. This is what we'll write it as B Vsat. And the lower trip point will be minus Vsat times the same factor R1 by R1 plus R2, which again will be written as minus B Vsat. So for any relaxation oscillator, the output will be high for some time and then the output will switch to low. It will remain at low for some time before coming back to high, and this keeps repeating forever as long as there is a power supply. So what is TH? It is tau ln 1 plus B by 1 minus B. In fact, for this circuit, TH and TL both will be identical because the time constant is always going to be R3 into C. So tau, whether the cap is getting charged or discharged, will always be equal to what? R3C. So the values of TH and TL will be identical. And the total time period is obviously the sum of TH and TL. Since TH and TL both are equal to tau ln 1 plus B by 1 minus B, the time period will be 2 tau times ln 1 plus B by 1 minus B. So what is tau? It is R3C. So 2 times R3, 2 times R3C times ln 1 plus B by 1 minus B. Anyway, let us get the value of 1 plus B by 1 minus B. So what is B? So B is R1 by R1 plus R2. So what is 1 plus B? 1 plus B must be 2R1 plus R2 by R1 plus R2. And what is 1 minus B going to be? Given that B is what? R1 by R1 plus R2. 1 minus B would be R2 by R1 plus R2. So we have 1 plus B, we also have 1 minus B. So what is 1 plus B upon 1 minus B? 2R1 plus R2 by R2, which is 1 plus 2R1 by R2. That's all. There is the time period of the square wave that is obtained at the output. Remember, at the output you will get a square wave which switches between Vsat and minus Vsat. So now you just have to pick up the right option. 2R3C ln 1 plus 2R1 by R2, which is option B. Is that correct? 2R3C ln 1 plus 2R1 by R2. So it is what? Option B. Okay. Look at the next question. For what is the small signal gain of the below circuit? Vn is the small signal input, V0 is the small signal output. There is a coupling capacitor. So is it not a common source amplifier? Yes or no? Input applied at the gate, output taken at the drain. It is a common source amplifier. In fact, it is the common source with source degeneration. So the given amplifier, it is what? Common source amplifier with source degeneration, where this 1 kilo ohm, it is the source degeneration resistance. This 5 kilo ohm, we will call it RD. You see, during AC analysis, this coupling capacitor acts like a short circuit. So this Vn will directly appear at the gate. Now this is a very standard circuit. So if there is VDD, Vi, V0, Rs, Rd, and assuming the transconductance to be Gm, and also assuming there is no channel length modulation, that is R0 tending to infinity. What is the small signal voltage gain of this particular common source amplifier with source degeneration? It is minus Gm Rd upon 1 plus Gm Rs. So what is Rd here? 5 kilo ohm. What is Rs here? 1 kilo ohm. It is also given that Gm tends to infinity. The transconductance tends to infinity. It only means that the transconductance is large. So if Gm tends to infinity, obviously 1 by Gm will tend to 0. That is the point. Now in this gain expression, V0 by Vi, let us divide both numerator and denominator by Gm. Then we will get minus Rd upon 1 by Gm plus Rs. Now let us use the fact that Gm tends to infinity, which means 1 by Gm will become 0. So the gain will be simply equal to minus Rd by Rs, which is minus 5 kilo ohms by 1 kilo ohm. So the final answer is minus 5, which is option A. Okay. Well, look at the next circuit. For the circuit below, find the value of the current Ix. Okay, let me draw the circuit. So this is 3K, this is also 3K, this is also 3K. And the current through this 3K is some Ix. And the question is what? To find the value of Ix. There is nothing in this. You see, what is the drop? Okay, let me call 3K as some R. Okay. What is the potential at this point from virtual short? This would be 0. What is the potential at this point? 4 volts. So how much is the current through 6K in this direction? 4 minus 0, 4 by 6K, which is 2 by 3 milliamps. So what is the drop across this 3K through which the current is Ix? Is it not Ix into R? So what is the potential at this point? It is Ix times R. Now what is the current through 3K from right to left? Ixr minus 0 by 3K, which is again R. So is it not simply Ix? And remember, for ideal op amp, the input current is 0. Now let us just write KCL at this point. See, if you notice, at this point 2 by 3 milliamps is entering, Ix is also entering, whereas 0 current is what leaving. So is it not Ix plus 2 by 3 milliamps equal to 0, which means Ix is what? Minus 2 by 3 milliamps, which is minus 0.67 milliamps, and that is option D. Look at the next question. Q1 and Q2 both are PNP transistors. They are saying they are perfectly matched. That means all parameters will be identical for both the transistors, assuming beta to be infinite. If beta tends to infinity, then the base current will tend to 0. And forward bias voltage drop in the diode. So V on, the cut-in voltage is 0.7 volts. You have to find this current I out. See, first of all, the two transistors, they are in parallel. The given circuit is a current mirror. So what is the principle of a current mirror? Identical transistors operating in active, connected in parallel, will have the same collector current. So if this is I out, then this will also be I out. And because the base currents are 0, this current both will be 0. Even this current will be 0. And then what? This drop will be 0.7. So what is the potential at this point? 5 minus 0.7, which is 4.3. Again, there will be a 0.7 volt drop across the diode. So what is the potential at this point? 3.6 volts. So how much is the current through this 1 kilo ohm resistor? Is it not 3.6 milliamps? And again, this current is same as what? I out. So obviously I out equal to what? 3.6 milliamps, which is option C. Okay, look at the next question. In the circuit below, find the terminals of X and Y. So X and Y, they are the two input terminals of the given op amp. Again, the requirement is what? The circuit should be having negative feedback. Again, for negative feedback, the loop gain must be negative, and so on. So how do you find it? See, first of all, at the output, you apply some test voltage Vt and also make the independent source 0. Now this current, both are input currents, so both will be 0. So what is the voltage or potential at the input terminal marked Y? I'll call it Vy. So this 1K and this 2K both will be in series. So from voltage division, Vy will be Vt into 2K by 1K plus 2K, which is 2 Vt by 3. And at the top, this 1K and this 1K both are in series. So what is Vx? Again, from voltage division, it is Vt by 2. And clearly, Vy is greater than Vx. Now, what is our requirement? The op amp must be in negative feedback. For the op amp to be in negative feedback, the output that is fed back to the minus input terminal should be greater than the output that is fed back to the plus input terminal. And here, Vy is greater than Vx. So obviously, Y should be the negative input terminal and X has to be the plus input terminal. Now let's find out which is the correct option. So X must be positive, Y must be negative, which is option C. Okay. Find the type of feedback in the circuit. First of all, the given circuit, is it not the non-inverting, is it not the non-inverting amplifier? Yes. So non-inverting amplifier, which is the feedback element? Is it not this 1 kilo ohm resistor? This 1 kilo ohm resistor, that is the feedback element. And you know, we have two simple rules to determine the type of feedback, which will work for most of the circuits. Okay. And for this circuit, those two rules will definitely work. So the B block is directly connected to the output. So it is voltage sampling. And the B block the feedback network is connected to the minus input terminal, whereas the input is applied at the plus input terminal. So clearly the B block or the feedback network is not directly connected to the input, which again means we are doing voltage mixing. So in a non-inverting amplifier, what takes place? Voltage sampling and voltage mixing. So voltage mixing is also called series mixing. Voltage sampling is also called shunt sampling. Now the same feedback can be called as series mixing, shunt sampling. So we just drop the two words mixing and sampling and we simply call it series shunt, which is option C. Okay. So non-inverting amplifier, we have series shunt type of feedback. Okay. A bipolar junction transistor BJT is always a current control device. FET is a voltage controlled device. So BJT is a current control device, which is option C. Okay. Again, there is some op-amp circuit. What kind of filter is realized by the below circuit? Again, the op-amp can be assumed to be ideal. I think these all pass. Anyway, let's find out. In this circuit also, all the three resistors are identical. I will label all of them as being some R. Again, R is what? 1 kilo ohm. Once again, I will create a copy of this. So now what? We'll just find the output or the gain at low frequency and also at high frequency. First, we'll find the gain at low frequency. Again, at low frequency, the capacitor can be removed because it behaves like an open circuit. Look at this. I simply remove the capacitor. Now, no current will flow in this R. So, no drop across this R. So, this VI will directly appear at the plus input terminal. Now, from virtual short, V minus will also be VI. Again, this current is 0. Even this current is 0. Because these two currents are 0, even this current will be 0. And the drop will be 0. So, V naught equal to VI. So, what is the gain at low frequency? It is 1. In fact, plus 1. In the same way, let us find the output at high frequency. Again, at high frequency, we can replace the capacitor with a short circuit. I'll just make the capacitor short circuit. Immediately, ground will be connected to the plus input terminal, which means V plus will become 0. Now again, from virtual short, even V minus will be 0. This current, being the input current, will be 0. So what is this current? VI by R. So what is this current? Also VI by R. So what is the drop across this R? VI. So what is V naught? Minus VI. If V naught is minus VI, what is the gain? Minus 1. So at both low and high frequencies, the magnitude of the gain, is it not same? At low frequency and also at high frequency, the magnitude of the gain is the same, but the sign of the gain is different. So which means at low frequency, the output and input are in phase, whereas at high frequency, the output and input are 180 degrees out of phase. So this is what is the behavior or the response of an all pass filter, which is option A. Okay, find V out in the below circuit. Assume op amp to be ideal. See, what you should understand from this is that between these 2 points, we have a input voltage source whose value is 1 volt. That is how you should understand the given circuit. I'll just draw the neat diagram of the given circuit. So look at this. Between the 2 input terminals, that is this point and this point, I have connected a voltage source of value 1 volt. Here also all the resistors are identical. Let them be R each, where again R is what, some 1 kilo ohm. Let's find the output voltage V0. Again, this op amp is in negative feedback, so virtual short will be valid. See, if you look at the plus input terminal, is it not directly connected to ground, which means V plus will be 0. Now from virtual short, even V minus will be 0. And these 2 points are virtually shorted. So it is as if we have a loop here. So what is the current in this loop? Will it not be 1 volt divided by the net resistance in the loop, which is 2R? So is it not 1 by 2R? So what is this current? 1 volt by 2R. Again, this current being 0. So even this current will be what? 1 volts by 2R. Now 1 volt by 2R current flowing through R will result in a voltage drop of 1 volt by 2R into R, which is half a volt or 0.5 volts. Now this is 0 volts. Then you go from plus to minus, you have to subtract the drop. So V0 will be minus 0.5 volts. So what is V0? Minus 0.5 volts, which is not among the given options. So I think 122nd question, mark should be granted to all, irrespective of your response, because the correct answer is V0 equal to minus 0.5 volts. Okay. Next one. For the 2 circuits to be equivalent, R should be equal to, first of all, there is the small signal equivalent of a MOSFET, in fact the NMOS transistor, of course when it operates in saturation. You see, in the given thing that is on the left hand side, what is the current flowing at the gate? 0, because after the gate terminal we just have an open circuit, so the current at the gate has to be 0. Now for the second small signal circuit to be equivalent to the first one, even in the second case the gate current has to be 0, and for that gate current to be 0, so obviously this current and this current both have to be equal. Now what is the current through R? Ohm's law, VGS by R, this must be equal to GM VGS. So obviously R must be equal to 1 by GM. This is very straightforward. Okay. So the correct option is option D. In fact, this is like the pi model and this is like the T model of the same device, which is the MOSFET. Okay. I think this question we already saw it. In the circuit below, find the, okay, this time they have asked you to find the value of V0. Earlier, in the last previous question, they asked you to decide which of the 2 terminals X and Y should be plus and which one should be minus, such that the op amp is in negative feedback. But in this question, they are saying that X and Y have been chosen such that the op amp is in negative feedback. In such a case, what is the value of the output voltage? I think I already told you in the earlier problem that Y must be the negative input terminal and X must be the positive input terminal. Taking this into consideration, let me draw the circuit. Okay, here correction. Y must be negative, X is positive. Okay. So this is 1K, this is 1K, this is 2K, this is 1K, this is 2 volts. Again, this is very straightforward because already we know the op amp is in negative feedback. We just have to use the principle of virtual short. V plus equal to V minus. What is this current? 0. What is this current? 0. Because this current is 0, these 2 currents will be equal. So from voltage division, the voltage at this point will be V0 by 2. Again, this 2K and this 1K will have the same current. In other words, they are in series. This 2K and this 1K, are they not in series between 2 volts and V0? So let us directly write the voltage at this point through that superposition thing. So voltage at this point will be 2 V0 by 3 plus 2 by 3. And this 2V0 by 3 plus 2 by 3 is nothing but V minus, whereas this V0 by 2 will be V plus. So here, in place of V plus, I'll write V0 by 2. In place of V minus, I'll write 2V0 by 3 plus 2 by 3. Now what is 1 by 2 minus 2 by 3? 1 by 2 minus 2 by 3, I think is minus V0 by 6 equal to 2 by 3. So I think V0 is minus 4 volts, which is option A. Okay. 14th question. A MOSFET biased in common drain is best suited for designing. See, common drain is same as common collector. Common collector is also called as emitter follower. In the same way, common drain is also called as source follower, and for both the amplifiers the voltage gain will be very close to 1. Only in the ideal case it would be 1, but in general the gain will be very close to 1.98 something, etc. Voltage gain 1, it is a voltage buffer. So common source and common emitter both are voltage amplifiers, whereas common gate and common base both are used as current buffers. Common drain, common collector, of course they are used as voltage buffers. So correct option is option C. Thank you.